Last time when we last saw each other, we were talking buffers, I think. Yes, in our never-ending journey through chapter 14 still. All right. This class is brought to you by chapter 14, I think. All right. So we talked about buffers. Obviously, we talked about buffers this morning as well. And again, in case you forgot since this morning, it is still a weak acid, and the salt of its conjugate base are a weak base, and the salt of its conjugate acid. We talked about obviously doing buffer problems, and typically speaking, that is our Henderson-Hasselbalch equation that we want to use, which is our pH is equal to our pKa plus the log of the base over the acid. Once again, our pKa minus the log of the Ka value. We also again saw that kind of POH version of it. And as I mentioned before, you can use it, and sometimes books will use it and stuff like that. But really, I would say probably in most cases, since you usually will want the pH value, you might as well just go into the Henderson-Hasselbalch equation and get the pH directly. So you just got to make sure, obviously, you have that pKa value, and you have the base on top when you do it, and the acid on the bottom. Again, the one we're referring to is the one that looks like this. It is the pKb, and it is flipped around the acid over the base if you choose to do that. But once again, you get the POH and not the pH out of that. The pKb minus the log of the Kb value. The relationship that we also saw that's sometimes helpful, pKa plus the pKb does equal 14. So sometimes if you do need the pKa value, but you only have the Kb given to you, you can calculate the pKb and subtract 14 to get the pKa value if you needed to. We started doing problems, and we talked about the idea that in a buffer problem, which is a common ion problem, you could use the Henderson-Hasselbalch equation, but you can still do an ice table if you choose to do that without doing the Henderson-Hasselbalch equation. And again, if you had some type of ice table, it would be like your acid dissociating. And the important part of this, as we talked about, is actually the initial part. You do need a number here, and you do need a number here again on both sides in order for it to be a buffer. Otherwise, if you don't have that number on the right-hand side, as we talked about, it's not a buffer. It's just going to be a weak acid problem, and you'll get the wrong one. So if you want to do the buffer through an ice table, you can still do it. But because buffers are common ions, and we have the acid not really breaking apart as much, our initial concentrations and our final concentrations of the buffer components are usually pretty much the same because there's not a big change happening. So you can go directly into your Henderson-Hasselbalch equation. An important concept that we also talked about was the idea that when we do add volume to something like a buffer, we do have to do the ice table in moles, right? Because moles remain constant, but the molarity changes. So whenever you're adding volume, you do have to do your ice table there in moles. And then after that ice table, it is good practice to convert back into molarity using the total volume that you added. Again, in most cases, you'll need the molarity at the back end of a calculation like that. The one place where you could leave it in moles and still get the right answer is if you kind of throw it back into the Henderson-Hasselbalch equation. But again, if you don't throw it right into the Henderson-Hasselbalch equation, you should probably convert it to molarity regardless. So you're always sort of in the right units, no matter what the situation is a good idea. Any questions on any of that there? So that means we left off here was clearly this was the one that you were going to do at home like over a week ago, and you still haven't done it. Pretty accurate, I imagine. Yes. All right. So why don't you do it? Yes, here, and then we'll continue on and see where we're at. I think I gave you a Ka value here for our friend NH4 plus. It's going to be our 5.6 times 10 to the minus 10. Look and see. So clearly it's a buffer because it says it's a buffer. But again, it will not always tell you it's a buffer. So we should hopefully be able to recognize sort of the relationship between those two guys, as ammonium chloride is ammonium and chloride. So again, this chloride is really just a spectator ion kind of hanging out, not doing much with the pH, as is obviously is neutral. But it is that NH4 plus and that NH3, which is really our weak base. And actually the NH4 plus is our conjugate acid in this case. That's going to make up the buffer. Since it is a buffer and we want really the pH before and after we do any type of addition, we can go directly into the Henderson-Hasselbalch equation. The pH here is our pKa plus the log of the base over the acid. I'm going to get my pKa from here minus the log 5.6 times 10 to the minus 10. I believe should give us a 925, I think. That's going to give us a 9.25 plus the log here. It's important to get the base on top. Which one is the base? It is NH3, as that's the Ka for this guy, which would make it obviously the acid part. Remember, the acid should have probably one more hydrogen, yes, so it could give it away, yeah. So that's going to be 0.3 divided by 0.36. And that will get us 0.3 divided by 0.36, a little log action there, plus 925. Means we're going to open up here with a 9.17 as our opening pH here of our buffer. It's basic. Perhaps some of you chose that earlier today for your buffer if you were in that 9-ish range, as that would be a good choice. Any questions on that? Now, again, if you chose to do an ice table, as I was talking earlier, you can do a, you could do a KB type of ice table. Where you would have NH4, oops, not without the extra H there, NH4 plus and a little OH minus in this case. And once again, you would need a number here and a number here, which obviously would be our 0.3 and our 0.36. If you did this one, though, you would need to use the KB value for NH3. And as I think was your question earlier, you would get the OH minus concentration when you would solve for X, which will get you to the POH and then to the pH. You also could have done the more acid sort of approach here, where you would use the Ka value that was given to you. And again, here you would flip it around and you would have your numbers like so. Here, if you did that table, you would have the H plus concentration if you solve for X. So as you can see, a variety of different ways you could kind of get to that answer. I would choose the Henderson-Hasselbalch because it's used a lot less room, I suppose, to sort of get yourself there. Any questions on either way there? Okay, so the second part of it is we're going to add some sodium hydroxide to this buffer. So we want to see what the pH is after we add, in this case, 80 milliliters of 0.05 molar sodium hydroxide to our 0.3 molar ammonia and our 0.36 molar ammonium chloride. And actually, we're going to add, that's the wrong way. We're going to add 20 milliliters of this to 80 milliliters of our buffer here. All right. So obviously, in this case, we're going to have some addition. We do need to do an ice table to figure out what is going on, how our buffer will change as a result of this addition. Remember that this is really the base part of your buffer, and that's your acid part of your buffer. That means when I take my sodium hydroxide, it is going to react with what thing here? It will react with, it's going to react with the acid part, which in this case is the NH4Cl. And when we do this, we're going to get a little sodium chloride, perhaps, a little ammonia as well, and maybe a little bit of water. Just going to keep writing stuff there, yes. But most importantly, we'll get this guy, right, and this guy here. Clearly, because I'm adding at this point, I need to do this in moles, right? So we need to get the moles of everybody. And Still this area here, I think, to do that. All right, so if we want to calculate the moles of everybody going on here, we will take our 0.02 liters, which is our 20 milliliters, convert it to liters. We're going to times it by the molarity of our sodium hydroxide, moles per liter. And that will give us for our sodium hydroxide, looks like 0.001 moles of sodium hydroxide. We have 80 milliliters of the buffer. So just so we're clear, that buffer is a grand total of 80 milliliters, and it has our buffer floating in there, right? So the 80 milliliters goes for both parts of our buffer. And that means that for our NH3, we have 0.08 liters times the molarity of our NH3 moles per liter. Going to get us 0.08 times 0.3, 0.024 moles of our NH3. We got the same volume happening there for our other part of our buffer, and that is 0.36 moles per liter. So 0.08 times 0.36 going to get us 0.0288 moles of our NH4 plus, basically. Any questions on those calculations? All right, now we got everybody going on. Let's start filling it in here. So ice table wise, we have our sodium hydroxide, which was 0.001. I didn't write too many zeros there. And these are again moles. We do have NH4, which is going to be 0.0288. And we do have some NH3, which is 0.024 moles. I'm not going to worry about sodium chloride because it's neutral. I'm not going to worry about water because it's not included. So again, I wouldn't put any type of numbers or X's in those spots. This is a buffer, which means what should happen? My sodium hydroxide should go away, right? So remember that typically speaking, when you do an ice table in moles, you actually do know the change part, and we do use a number, and it should be the moles of our sodium hydroxide should be our change. That means we will minus that across the board here. We will also plus it on this side of the board. That is going to get us hopefully a buffer that used up all the sodium hydroxide. That means that we will end up with here 0.0278 moles of this guy. Bless you. 0.0240 minus plus. Kind of like minus, but not so much. 0.025 moles of this guy. At this point, once you're done with this table, you should really convert it back to molarity. So we're going to convert it back to molarity at this point by using our total volume. We had 80 milliliters of our buffer. We added 20 milliliters of the sodium hydroxide. That's going to give us a total volume of 100 milliliters in this case. That means we're going to divide each of these guys by 0.1 liters, which is 100 milliliters, right? That's going to give us 0.278 molar and 0.250 molar at this point. Any questions on that so far? Or on the ice table, how we got the total volume? Obviously, in this example, unlike the previous example, we are not holding volume constant. So obviously, you need to take all that into consideration in this case. If you are still not sure, one more ding just to make sure. If you are still not sure what is going on at this point, again, you can use your ice table to help you out. If you look at what is left at this point, we pretty much have just those two things left over. These two things are still a buffer. Yeah. So again, if you're not sure, you can see what's left over in your ice table. Hopefully still recognize it as a buffer. That means if I want the pH of my buffer, I should go back into the Henderson-Hasselbalch equation. You could, again, also do some ice tables if you wanted to. We're going to go with our pH is our 9.25 plus the log of our base, which in this case is this guy here, 0.250 divided by 0.278. We're going to take 0.250 divided by 0.278. We're going to do a little log action of it, and we're going to add it to 9.25, looks like. And we're going to end up with a 9.20 here as our pH of our buffer at this point. The 0.1 liters down here you're talking? So we do always want to kind of convert after that ice table back into molarity. So it's actually the total volume of what we added. So we started with 80 milliliters of the buffer, and we added 20 milliliters of the sodium hydroxide. So that gave us a total volume of what would be like sitting in the beaker at this point of 100. Yeah. Why are we using a 9.25? The 9.17 is the initial pH. Yeah. Other questions? All right, a couple of things on our answers. First off, was the buffer pretty good? Yeah, we started at 9.17. We added 20 milliliters of sodium hydroxide to it. It budged a whopping point, whatever that is, 1.3 of a pH unit. Did it move at least in the correct direction? It did, because we added sodium hydroxide with a base, which means we should expect, after we add the base, not a big jump in pH, but it should tick upwards, right? Because we're adding base to it. So these are things you want to look at to make sure you didn't invert some numbers. So again, if you did this calculation, you got less than 9.17, that really shouldn't make sense to you, because you're adding a base, which means your pH should go up a little bit. It shouldn't jump if it's a good buffer, which I guess this would be a pretty good buffer in this case. Question? No. So in this case, I did use, obviously, like I said before, the Henderson-Hasselbalch equation, and I just kind of did it through the acid way. You absolutely could do this one again through the base way using the POH version of it. But again, at the end, you got to subtract a 14 to get back here as well. If you did the POH version of it, again, you would be using the PKB value, and you want the acid over the base and then acid subtract it, but it will work the same way. Any questions on buffers, how to calculate the pH of buffers with and without adding stuff to it? All right. Yeah. Say again. You always want to do an ice table in moles whenever you're adding basically volumes together. So like you have a solution sitting there, you're going to add something to it. You always want to do definitely the first ice table in moles and then convert it to molarity. So in terms of buffers, that always happens when you kind of have a buffer and you're going to add either more acid or base to it. As we're going to talk about next, that happens consistently as we're doing titrations. We're constantly adding the volume. So whenever the volume is really changing, you really want to do kind of your work in moles, because that should remain constant, and then convert it to molarity at the end. Other questions? All right. So now that we're buffer professionals. Nervous to laugh, that makes me feel good. All right, then let's talk about everybody's favorite thing, which is titrations. Fond memory. Let's just take a moment and remember. It's Chem 50, you're titrating, you're feeling good about it, you add 1 drop and it's super pink. But maybe you still feel good about it at that point. That's all right. We'll talk about why that happens as well here in our journey through titrations, and we will start titrating very shortly in lab. The good news is you're just going to sail through that endpoint and not worry about it. You don't have to stop at that point. So a titration is obviously a technique where, typically speaking, we have one solution that is sort of a known solution, and we add it to a unknown solution. And obviously, we could calculate a lot of things. We could calculate things like molarities of unknown solutions, molar masses of unknown solutions, using stoichiometry and solution stoichiometry. So when we do a titration, typically speaking, we have a wonderfully drawn burette there. And we added a solution to another And we typically will titrate to what is known as the equivalence point. And in an acid-base titration, the equivalence point is really the point where the moles of the acid equals the moles of the base. So that is the exact point where, for example, if you're adding base to your acid, you've added exactly enough to use up all the acid you started with. And if you're adding acid to a base, same thing. And that's what the equivalence point is. The end point of a titration, which you sometimes hear people refer to, the end point of a titration is pretty much what it sounds like. It's where you stop your titration. And if you're doing a good titration, hopefully the end point and the equivalence point should be close to one another. If you're not doing a great titration, then maybe they're not very close to one another. So how do we know when we should stop the titration? We should stop titration when we see a color change, and we use indicators to help us do that. And as we'll talk about with indicators, indicators actually work over a pH range. So this is our friend phenolphthalein. Yes, bonus question, spell that. That is like phenolphthalein, something like that. That works, give or take a letter or two. It's pretty close, I'm almost sure. Phenolphthalein, by the way, is what color in acidic solution? No. Are you asking the question or no? I'm not sure. All we know is pink is the right answer for any question that involves phenolphthalein and titrations. Gosh forbid, you could do a titration without phenolphthalein, by the way. You don't have to get to turn pink. All right. Well, it is colorless, yes, in acidic solutions. By the way, in neutral solutions, what is it? That's still colorless. In basic solutions, it is. No, it's still economics. Yeah, it's pink. Okay, so phenolphthalein works over actually a pH range of like 8.3 to like 10-ish. And right there at 8.3, it is colorless, but then becomes pink, which is why when they yell at you when you titrate, you need to stop when it is the lightest shade of pink, like you got to hold it up to the whiteboard to see the pink in the flash, right? People do that, like hold up the. Do you see the pink color as they're running around the room? I find that when the instructor says extra and credit, those two magical words, people can automatically get light pink very quickly when they're titrating. Before that, it's like dark pink everywhere, yes, and stuff. So that's why they usually will tell you, in the same sentence where they tell you to do a half a drop where you use your wash bottle. They will usually tell you that what you're looking for is the lightest shade of pink that will persist, right? And again, so light that you almost have to put it against some type of background to see that. And that is because that would put you in this area in terms of pH, which is probably in your vinegar and sodium hydroxide titration is close to the equivalence point. Dark pink, and why they yell at you perhaps dark pink, did they make you redo your titration so you got dark pink? Oh, bad teachers. I'm just kidding. We cut that out of the recording as well. They're like really gonna fire me now. So you'll have somebody new next week. I'm sure they're lovely people. I'm sure. All right. So they tell you to go not dark pink, and they're not happy with you. Be like way over here, right, in dark pink and stuff like that. But we'll talk about why maybe you didn't have to retitrate and stuff in just a second. So yeah. It kind of stays that dark pink, yeah, for the most part. We do want to, as we were talking about, for example, indicators, and we're having fun here with phenolphthalein, but when we do choose an actual indicator, we clearly want to be able to see the color change occur right near your equivalence point. That's why phenolphthalein works really well for those titrations that you did in Chem 50, but they would be really crappy choice for something where the equivalence point's acidic, right? Because they're going to change color, so you want to know where to stop. So we do choose an indicator based on the equivalence point of the titration, the pH at the equivalence point of the titration that you're doing, so that you could visually obviously see that color change, so that you know that you should stop your titration. So that's why I said earlier, not all titrations will use phenolphthalein, for example. Other ones will use ones that turn yellow or blue or other colors because they change at different pHs and stuff like that. So let us talk about titrations here, shall we? That is a titration curve. And the first type of titration we're going to talk about is our friend, the strong acid and strong base titration. And this is a typical titration curve that you will make come that titration experiment. And as you can see, we go past the equivalence point, which is really nice. So when we have a strong acid and strong base, say something like hydrochloric acid plus a little sodium hydroxide action there, gonna give us some water, I think. There we go. And a little sodium chloride happening. So just for orientation purposes here, up in our burette in this titration is the sodium hydroxide. We are adding it to our hydrochloric acid in this case. So we're going to start dropping. So when we look at a titration curve, it's sometimes referred to as like an S curve, and that is typically what we see here in this picture. And there's actually really kind of 4 parts to a titration curve and 4 parts as to where you could calculate the pH. And really, you could calculate the pH anywhere along the journey here. So let's start with really the first part of the titration curve, which is right about here. And that is before we add sodium hydroxide. So this is really before the titration begins. So if I want to know the pH of my solution here before I add any sodium hydroxide to it, what is the only thing sitting in my beaker, flask, whatever piece of glassware you're using there? The only thing in there is HCl, right? And HCl is what type of acid? The strong acid. So if I wanted to know the pH of this strong acid, because it's a strong acid, we know that it will 100% break apart into H plus and Cl minus in this case. And if I know the concentration of the HCl, I will know the concentration of the H plus in this case. And that means I could directly go into our pH equation at this point. So this is basically what we have going on here is the pH of a strong acid at this point. And that's how you would get your kind of opening pH here before you started. Again, because it's a strong acid, you just get the H plus concentration right into the pH. Not too bad so far. Good so far. All right. Now you're encouraged to start the titration. Turn that thing on. Let it drop slowly. Or just crank it open and let it shoot out like I titrate, right? And you'll be good. So anywhere from the first drop to right before the equivalence point there, that's sort of the second part of our titration curve. And as we can see at this point, we're starting to add some sodium hydroxide. So we're starting to see the pH start to rise a little bit there as we're going through. So in this case, we're going to add something. I don't know where I'm going. I'm going somewhere. I can go here, I think. There we go. So in this case, at the second part of the titration curve, once we start adding sodium hydroxide, and this is before the equivalence point, we have a reaction that's going to happen between our sodium hydroxide we're adding and our hydrochloric acid that's in there. So we will need to do an ice table at this point. So we have to have a reaction between our hydrochloric acid and the sodium hydroxide that we're adding. And we're going to get, again, here a little bit of water and a little sodium chloride in this case, right? Okay, so I need to do this ice table in molarity or moles. Yeah, because in a titration, you're doing nothing but continuously adding volume, which means the molarity is constantly changing, but the moles will be the same. All right, so we're going to do a made-up calculation here. I'm making up this number. That is where the number comes from. In case you want to ask me later where the number came from, you could watch this video and you'll hear I just made up this number. So I'm going to pretend that I am starting with 4 moles of my HCl, which is my made-up number. I just did that right there with 4. And I am also going to make up the moles of my sodium hydroxide here, right? And if I happen to be before the equivalence point, should the moles of what I'm adding, which is basically the sodium hydroxide, and the HCl is basically what I'm starting with, right? Should the moles of the sodium hydroxide be less than, equal to, or greater than the moles of the HCl? It should be less than, because we are before the equivalence point. Because we know at the equivalence point, the moles of the acid and the moles of the base are equal to each other. So we know that it has to be less than before we reach that point. So once again, I'm going to make up a number like 2, seems like a nice number. And I'm going to have like nothing much going on this side. Bless you. At this point, we're going to have a change that's going to occur. And at this point, the one that should get used up is... It is, because it's like the limiting reagent, right? That's like the limiting reagent at this point. That's like our excess reagent. So the change here also needs to be, logically speaking, the smaller number. Otherwise, you end up with a negative number, which is not good either, right? So that is going to get us here 2 moles of this guy, nothing of that guy, 2 moles of this guy. At this point, just like we did with the buffers, we should convert these things back into molarity by dividing by the total volume. This would be obviously the total volume. And the total volume is how much HCl I started with, like in the beaker, right? And how much of the sodium hydroxide I added from the burette to get me there. First off, any questions on the ice table here? All right, so if you're still not really sure what we should do at this point, we can look at the ice table here and help us out. We basically got this guy left, which you might have. We have that guy left. First off, is that a buffer? It is not a buffer, because HCl is a strong acid, so it cannot be a buffer. Out of the guy on the right there, which is a salt, which is sodium chloride, what type of salt is that? It is a neutral salt, which means really not going to do much there for the pH at this point, because it's neutral. Comes from basically a strong acid and a strong base. That means really the only thing left that could affect the pH is my HCl. And the purpose of this ice table, which you need to do in this type of titration, is you need to do an ice table to figure out what is your molarity of your strong acid after it reacts. And then at that point, you could go into your pH equation. So it does require, once you start the titration, to do an ice table. Again, the purpose of this ice table is really to figure out the new concentration of your strong acid after it reacted with some of the sodium hydroxide that you added. You should convert it back to molarity, because you kind of need molarity when you go into the pH. So this is what I was talking about earlier. It's just really good practice to convert it back to molarity after that first ice table. That way, in pretty much all cases, you'll be in the right units that you need. And then we would have our pH, which should be a little bit more basic-y than, a little higher than where we started. Yeah, not really basic pH, but you should start to see the pH start to rise, as obviously you're adding some sodium hydroxide. So before the titration begins, you have just a strong acid. You could go right into the pH equation to calculate the pH of it. As you start titrating, it requires one ice table to figure out how the concentration of your strong acid has changed. Ready for the next part? Here we go. Part number 3, which is our equivalence point. Now, this typically is what happens here. As we approach the equivalence point, as you can maybe see here, as I approach the equivalence point, I start to go pretty vertical. Yeah, and even past the equivalence point, I go pretty vertical. This is the answer to the question of, I only added 1 drop. And it went pink. All capitals. That's like I'm yelling, I hear when I write it in all capitals. So it turned really pink. Yes. So why is that? What happens as I go vertical on this graph? Does the pH change a lot? Yeah, the pH from here to here is a lot of change in pH. Did the volume change a lot? Volume did not change a lot. And why does that affect your phenolphthalein? Because 8.3 here to like 10, that is colorless to pink, which means even if you added just like 1 drop and you're really careful, you could be over here, right? In terms of your pH, which means your color and your indicator is going to be super pink, right? But is there a big difference in the volume of there to where the actual equivalence point is? No, which is why you really didn't have to probably redo your titrations if you were really careful, because you probably were still in the same ballpark of your equivalence point volume. Mean teachers, you see, this is why we need to go talk to these teachers, right? But why do they tell you that? Because they're not really mean. They're telling you that because they don't know how you did the titration. They're not standing over you, hopefully. I don't know what's going on there. But you could also get that wonderful color of pink with a pH is over here, right? That's going to be the same pink. And now are you close to your equivalence point volume? Not very much, right? So there is no real distinction between beautiful dark pink and super dark pink, right? It's just pink at some point, beautiful shade of fuchsia, whatever color you like to call it at that point. So if you were really careful when you did your titrations and you really were kind of doing drop by drop as you approach the equivalence point, and maybe you missed it by 1 drop, in the grand scheme of things, not going to make a big difference in your calculation because you would have basically the same volume. But if you weren't very careful and a bad titration person like me and just opened it up, walked away, came back, shut it off, and it was dark pink, who knows where you're at, really? But I was always the first one done with titrations because, places to be, people to see, you know what I'm saying? So, I don't have all day to do the titrations. So that's why they really yell at you. Usually like, hey, hopefully they're not really yelling, but they encourage you to stop at the lightest shade of pink. And if you went too dark, they will sometimes tell you has to retitrate. But the truthful answer is if you were really careful and you missed it by a drop, you're really still in the same volume as your equivalence point, which is what you were shooting for. You really didn't need to go retitrate the whole thing again. But if you weren't careful, you could find yourself very, very far from the equivalence point volume. Any questions on that there? I'm gonna have a lot to edit out of this video later. All right, so let's talk about number 3 here. So let's talk what happens in terms of the equivalence point. So if we are at the equivalence point here, we'll wrap it up with this last little speech here at the equivalence point. We have our same reaction, which is our HCl and our sodium hydroxide, giving us our water and our sodium chloride in this case. So once again, I'm going to use my made up numbers, which is, again, I am starting with here my nice made up number of 4 moles. That means that I'm adding my sodium hydroxide to it. And if I'm at the equivalence point, the moles should be 4. Yeah, that's a good number to know. It's the same number. This would be 0 in this case, which would mean that you really can't mess up here, I hope, because the change here should be 4, and that's the only number that is present at this point. That's going to give me 0, that guy, 0, that guy. We're going to get 4 of this guy, which we could convert back to molarity. So we see at the equivalence point, the only thing left here is our sodium chloride, which is a salt, and it is, as you mentioned before, a neutral salt, which means at the equivalence point, the pH of this type of titration should be 7. So we would expect at the equivalence point of this type of titration for it to be a pH of 7, because basically the only thing left over at that point is a neutral salt. Any questions on that there? All right, I think we'll lay it up